This video will be a technical demonstration of my homemade 8-bit computer, which I lovingly refer to as Janknet. So the very first part is going to be a timer and a counter. So the timer is going to do very simple on-off pulses, and it's going to make sure that the counter counts up from 0 to 255. Each one of those different numbers that it counts to is going to be a different number for the program register. The program register, or program module, sometimes also called the control module, has two different modes. One, where you input into the system, give it different instructions with these 8 binary digits that are fed into this memory part here. And another part where they go over there and then they are fed down and output into the system. The ALU, which stands for Arithmetic Logic Unit, is basically the math part of the computer. It can do addition and subtraction. The memory is used with the ALU and is used to store important numbers for later. Also notice that the chip that holds the memory is the exact same one that is used to store the program. The only difference is that the memory has a register here for the address of the words, whereas the memory for the program uses the counters instead. This basically means the memory can be used to store anything in any slot at once, whereas the program has a specific sequence it has to go through. Okay, I've gone and turned the computer on. You can see a pulsing LED in the back. That is the clock, and that is an indicator light for when there's a clock pulse. Right now, though, it's not. Even though the clock is running, nothing should be incrementing. I've gone and written a short Fibonacci sequence code here. This code will run and give us a couple of numbers in the Fibonacci sequence. There's 3 parts to the code: the count, instructions, and pseudocode. The count is going to increment every time there's a clock pulse, and at each increment it's going to activate instructions corresponding to its number. The instructions are 8 binary digits that control what the computer does. I've written some pseudocode to help understand what's going on within the computer. It starts at position 0, which has nothing programmed onto it, because I needed to not do anything when I reset the computer. It's going to load 0 into the input register from control, and then it's going to load 0 into A and B. This is basically a precaution, because if I ever reset the code and there's something loaded into the registers, it's going to interfere with the program. Think about it like when you're programming and you just do a clear command at the beginning. Now after that, it's going to increment, output ALU, and then load to B. So what this is going to do is, since I can't input any odd numbers in, I can use the increment to turn any even number I put in to odd. Now, what this is basically going to do, because I don't have enough pins, what this is basically going to do is turn the 0 I put in into a 1. And that's going to be the 1 that we feed in as the first part of our Fibonacci sequence. Now, the output ALU and then load to B is basically going to be it recursively putting its output back into the input counter. And then you're going to see output ALU to register A or B alternating over and over again, because basically that's all the Fibonacci sequence is an alternation of going back and forth between adding numbers, and it uses the number it just had as part of its next one. So let's see it in action. Alright, now that we've explored how the clear works and how the registers work up to an extent, let's see the code in action. Now, this is partially just because my board is janky, because, can't make all of this mess of wires without something being a little bit off. But I'm only going to go up to 4, then switch to the input-output. This is partially because before a certain point, if I have this on the input-output measures, then it's going to count as a grounding for the inputs itself, and it can sometimes interfere with the measurements. But should work when we measure it past that. Alright, so we're going to go up to 4, 2, 3, 4. And then we're going to switch to the board itself. Now, you can see that there's already a 1 there, And that is because of the increment ALU, output ALU. You can also see that it's plinking because the output of the ALU is also tied in time with the timer. Now we will increment it. 2, 3, 5, 8, 13. And then past that, stops giving output because I didn't write code past that point. But as you can see, we could even go further, but that's, well, see that? Because sometimes random code gets stuck in the command module if nothing's been written there, and just crazy stuff starts happening.